You know what? I've been going this whole time and I haven't had this on. You guys didn't tell me. So we've been doing this. So hopefully everybody followed us, so that's okay. If you want to look at it again, you just won't hear my voice until this point. Okay. Any other things you would like to go over? Can't do all of them. I want you to try on your own. We've done a couple. Oh, would you please go to your parts per million page, because I know there's a mistake on that. And I know it's caused a lot of stress for everybody. The one that you got last time, the worksheet for the parts per million, but we were out. And it's number 6. Number 6 was written wrong on the first part. All of those milliliters on the first should be milligrams. All of those first ones should be milligrams. So 2 milligrams of solid, 0.00000 milligrams, 0.005 milligrams, 0.03 milligrams. So if you change those to milligrams, all you have to do is get it in milligrams per liter, and that's parts per million. So you're going to divide it. So milligrams divided by liters will give you parts per million. Okay? It's so much easier, I know. Okay? So milligrams. Milligrams. So change all the milliliters, the first ones, to milligrams. So 2 milliliters should be 2 milligrams. 0.0009 milliliters should be milligrams. Okay? Actually, it's not. If you look at this one right here, if you look at this right here, it actually says if you take, where is it? I can't see it this close. Right here. 1 milligram per milliliter is 1 part per million. Okay, I think I've actually got it over here. I can show you real quick. Okay, yep, I've got it right here. I can show you. Maybe there. Okay, so yes, sir. Yes, quickly. Okay, so right here it said on your packet at the very first, 1 milligram divided by a liter equals 1 part per million. So if you can get it in milligrams divided by liters, you got it. Okay? Divide by 1,000. Yep. Okay, while I've got this up, I'm going to show you, did you guys see this picture in the newspaper? This is the mine tailings spill that we were talking about with parts per million in southern, it's actually a Colorado mine, but it actually goes into Lake Powell. I'm going to bring this back up like this. So the the House details EPA missteps in Colorado mine spill. And I thought it was interesting here. Look at this. I'm going to bring it down. They dumped more than 880,000 pounds of heavy metals into the Colorado River. Whoa. Because if you look at these right here, these are collection ponds as you come out of a mine. They collect the pond and they sort of just let the top part come off and the heavy metal settle to the bottom. Well, they broke. And so all of it came into it. And so now what they've got is they've got several different ones set up before it gets down to where it goes into the river. The problem is it's heavier, it sinks. What do fish eat? Bottom feeders eat on the bottom, which is the heavy metals. And so that's why tuna is getting more mercury in it, because that's where mercury settles, is the bottom. And then bigger fish feed on them, and it just goes up the food chain. So, and if you happen to drink this water, you now become part of the food chain. Are you getting sued? Yeah. So this is that. When I saw that, 80,000 pounds of heavy metal into the Colorado River. 80,000. 880,000. That is like, I mean, think about how many pounds you are. Okay, and how much water does a river have? I mean, the Colorado River, yeah, it's a fairly decent river, but it's not real huge. And they put that much? Whoa, Okay, anyway, thought that was interesting. I thought with what we were doing and learning about, I thought I'd bring it in. Okay, any others? Yes, sir.
If it's an all-natural metal, so it's supposed to be nature, then what's the deal?
The problem is it's been mined, so it's been refined, and because it's been refined and it's been concentrated, it's not how we would be found in nature. So if it was just runoff, like in Idaho, they have a lot of selenium in their soil. And so when they have small streams get to bigger streams, they end up with some areas having very high concentration of selenium, which is not good for us. We need a trace amount. And too much of a good thing is bad. You've heard that? You know, a little bit of fluoride is good, but if you go and drink a gallon of it, you'll probably die. Yeah, you will die. Okay? So there's a difference between little and a lot, and that is like a lot. Okay? All right. So let's go on. Grab out your notes. I want you to try those things. What I'm going to do is I'm not going to count anything late until the day of the test. If you don't get it in by the day of the test, okay, and we actually added one more day for the unit. Test is next Friday. Okay? All right, so grab out your notes. Let's go through the rest of the notes. Yes, the review assignment needs to be done by the day of the test. So this is how it will work. We'll finish notes today. We'll do pre-lab for the lab next time. Okay? And you have your colligative assignment. We probably won't get to that today. First period didn't. It's okay. We'll have next time to finish up that and your review assignment, answer any questions. Well, not the next time. Next time we'll be in lab. And by the way, we'll deal with that in a minute. I almost told you a secret, but I won't tell you until the right time. After we do the lab next time, then we'll do a review Kahoot. And then the next time we come, we'll finish doing any assignments, or maybe I'll wait and do the review Kahoot on that next day that we've opened up and give you time to work on your assignments in class next time and a little bit the next time. Does that make sense? So we spread it out a little bit. Okay, so here we go. Solutions, day 4. You got your notes out? Ready to fill in the last part of your notes? Yeah. Okay. So you guys need to help me. If it doesn't fill in all the notes, then we need to Tiankum, you with me? Okay, just checking. Here we go. So there's things that affect salvation. No, I didn't say anything about Jesus. Okay, I said salvation, not salvation, salvation. Okay? Salvation is how fast things can dissolve. Okay? So how fast things can dissolve. What things help? Well, I think about the Kool-Aid, making the Kool-Aid. If I'm making the Kool-Aid, I got to stir it. I can't just dump everything together and say, yay, Kool-Aid. No. I'll have too yucky at the top and too sweet at the bottom, right? I got to stir the thing to get it to all solvate. Second thing is, if I tried to make Kool-Aid with sugar cubes, it would take a lot longer than if I tried to make it with powdered sugar, right? Powdered sugar would dissolve real fast. So particle size, particle size changes. Temperature, if I made Kool-Aid with hot water, then it would dissolve that sugar real quick. I wouldn't like to drink it because I don't like hot Kool-Aid, but that's what my mom used to give us when we were sick to our stomachs, was hot Kool-Aid. So that brings back really bad memories, okay? My mom would make sugar Jello water for us when we were sick. Yeah. It's okay. It was an old-fashioned electrolyte thing, okay? So we're going to talk about these 3 things. Now, in your notes, it just lists these right here. Agitation. What did I say agitation was? Stirring, mixing. So put another word there because you've got to know what agitation is. Agitation means to stir it or to mix it. Okay? Now this is the one that first period struggled with. How would I define surface area? The area around an object. Okay, the area around the object, or the outside area of an object, or the amount of surface that can react, right? So the outside surface of an area. Okay, so put a definition that makes sense to you. So just like the sugar cube, it doesn't have many outside surfaces, but the powdered sugar are small particles having a lot of surface overall. Okay, and the last one was temperature. Temperature, for the most part, if I increase it, things will dissolve faster. But those are endothermic processes. Oh no, another word we used last unit. What was endo? Put heat into it. So if a process wants me to put heat into it, if I put more heat into it, it's going to go faster, right? But what if it's an exothermic process? It's giving off heat. So if I put heat into it and it wants to give off heat, what's it going to do? It's going to go backwards. It's going to say, I want to give off heat to make my product, but you're giving me heat, so I'm going to go back to my reactants. Okay? So it's going to force it back to its reactants. So if a process is exothermic and I increase the temperature, it's actually going to slow down the rate of solvation. If it is endothermic, then it's going to increase it. Yes, ma'am?
Wait, so is that why, like, when you're making, like, a thin pie or something, if you, like, get the heat too fast, it'll scramble the eggs?
Mm-hmm. Okay. That's one of the reasons, yeah. You got to do it slow. Okay, you ready? Moving on. Okay, solubility. Solubility. I like these pictures over here. They help me understand it a little bit better. So as I look at an unsaturated solution, I'm having problems with alliterations. Okay, unsaturated solution, I could dissolve more in it. Sort of like my kids with the Kool-Aid. They say, oh, one cup of sugar is not enough. You need 2, you need 3. And then you end up with a saturated solution where I can't dissolve any more sugar in it, right? We make candy by using supersaturated solution. We put some sugar and some water with some flavoring, and we heat it up on the stove, and we stir it. Now, if we want good hard candy or divinity, we want to make sure we cool it slowly. Because if we cool it too fast, what happens is you get sugar crystals, and it just sort of ruins the candy. Well, same thing with a saturated solution. If I cool it too fast, or if I put in a seed crystal, then I get crystals. Okay? So I'm going to show you a little video here on it. Let's see if I can bring it up. It always goes to my other screen. So pull it over. It's thinking about it. There we go. Hopefully it will come up. This is something that you can do while this is coming up. I'm going to tell you how to do it. You can get a liter of vinegar and a teaspoon of baking soda. You guys all know this reaction, right? What happens? It bubbles. What you have to do is add the baking soda slow enough to the vinegar that it doesn't boil over, and do it in a pot that you can put on the stove. Then heat that up to the point where, I don't know why I've got 2 of them going. Heat that up until it goes down until it gets just okay, heat it up till it just gets, why is it not letting me full screen? There we go. So heat it up until it just gets a little film on it, and then pour it into a clean dish. He's actually got a seed crystal that he put in the bottom of that we didn't see when he poured it. It now is crystallizing. So this is what we call sodium acetate that you can make from baking soda and vinegar. So it crystallizes. This is a supersaturated solution. You can do it at home. It takes some time. I'll tell you again. Now watch what he's going to do. He's going to pour some more sodium acetate, saturated solution, onto this and see what happens. That reminds you of going to like Mount Timpanogos or something like that with the stalagmites and stalagmites. You guys can do this at home. It's just baking soda and vinegar, and you just heat it till it's just a little bit left. A liter of vinegar and a teaspoon of baking soda. It's actually what they call hot ice because it gives off heat. Now watch what he's going to do here. It's pretty cool. We'll just take a minute. He's got another petri dish here. So you can do this in just a bake dish. You ever had the hand warmers that you can reuse and heat up? That's what's inside of it. It's sodium acetate. And he keeps going. He wants to see how high he can make this tower. He doesn't have a firm foundation, you're right. Okay, now, he's going to do this over here. This one did not, this is a clean dish. So he's just pouring it in. Nothing will happen unless you have a seed crystal or a little piece of something. So what he's going to do is he's going to take part of the other crystal that he just made. He just put a piece of that tower he made. Now look. He just had a little teeny piece of sand or dirt. Pretty cool, huh? I don't know if marble would. It just needs to be something with a little bit of particle in it that will set it off. Table salt. Well, now remember you got to make the supersaturated solution. I'm going to kill this. You got to make the supersaturated solution first. So to make the supersaturated solution in a pan in your kitchen, you take a liter of vinegar, and to it you slowly add a teaspoon of baking soda. Then you have to heat it and let it boil down until you see sort of a skin like form on the top. And then you want to pour it directly into a clean, very, very clean container and let it cool down on its own. Don't touch it. Then you want to take something and put just a little bit of baking soda or a little bit of piece of salt on something and start pouring, and it will start going like that. It's way awesome. But it is a little tricky. It takes a couple of times to get it right. But this is a supersaturated solution where they've just dropped a piece into a flask and it's gone off. All right, so colligative properties. This is the next part we're working with. There are 4 colligative properties. I'm going to go through each one real quick and then we'll go through each one separately a little bit more in depth. So this is what happens. Colligative properties are what happen when I add the solute to the solvent. This is what happens to that solution. The first thing is vapor pressure decreases. That means basically my boiling point is lower happens at a lower pressure, okay? It's not that it's lower, but it happens at a lower pressure, okay? My melting point decreases, okay? My boiling point increases. That's why I put salt in water to make my mac and cheese, so the boiling point goes up higher. And osmosis is possible, or osmotic pressure. This is important when how our kidneys function. Okay, we'll talk about each one of these separately here in a minute. These 4 things are called colligative properties. They depend on the number of solute particles relative to the solvent particles. So on this one, we're going to need to use molality. Okay, molarity will not work here. We need to use molality. Okay, and remember molality is that little cursive. I did a little bit too much of the. No, that's that one. That's the moles of solute versus divided by kilograms of solvent. Okay. All right, so let's talk about the first one, vapor pressure lowering. We've worked with phase diagrams on this lab, or this unit. Notice the dotted line here. This is what happens when I add, like to water, I add salt or sugar. What are you noticing with the dotted lines up here? Okay, the pressure is lower, right, on each of these things. So I can boil at a lower temperature, but as I get on this side, what happens to the boiling point? If I go across here, what happens to the boiling point? Oh, I'm higher, right? So this becomes what happens when I have a phase diagram showing colligative properties. What happened to the sublimation line? Sublimation line didn't do anything. That's right here. What else went down? What's this point right here called? Triple point. My triple point changed. Okay, so let's go on to this next one, osmotic pressure. Have any of you guys taken a bath or gone swimming and you come out and you got granny hands? Okay, that's part of osmotic pressure. Your skin is acting like a semi-permeable membrane and things are passing in and out. You're trying to dilute or trying to change the concentration that's around you. So things are leaving you to try and dilute something else. So if I have salt water to fresh water, what's going to happen? If I have high solute to low solute, what's going to happen? So I'm trying to make them even. That's what osmotic pressure says. So the amount of pressure that goes through that, or the amount of things that go through that semi-permeable membrane, that will give me a pressure. Okay? Put the phone away, please. Okay? Change in boiling point. We already talked about this a little bit. How many are backpackers? Ever been backpacking, camping? Okay, if you go up in the high Uintas or you go up high in the mountains, first time mistake of backpacker is to take noodles. Why? Well, when you get up high in the mountains, the boiling point goes lower. So as you go to boil your noodles, you can boil them and boil them and boil them, and all they do is turn into a mushy muck. They never cook. They just sort of become soggy nasty because it doesn't get hot enough. So you can put tons of salt in to try and raise the temperature, and then you got a salty mess, and then you have to rinse it off. And if you're backpacking, you don't have a lot of water to rinse, so you have to go pump. It's just a mess. So seasoned backpackers know not to take noodles when you go, okay, or to take them already prepackaged in the MREs or whatever, or something like that. Dehydrated food is a lot easier to eat and feel happy about when you eating it. This is the back of antifreeze can. We use antifreeze in our cars to change the boiling point. So we're not driving down the road and all of a sudden our car's not working because all the water's boiled out, right? So we use antifreeze. It's also called ethylene glycol. We also put ethylene glycol in our cars to lower the freezing point so that we don't go out when it's 0 degrees outside and we have a frozen car and nothing works. So there's a lot of things that we do. So freezing point going down. Changing freezing point. So we talked about the antifreeze. We also put salt on the roads so we can lower the freezing point of the ice so that it will melt. Okay, we also use salt to make ice cream. Okay. So here's a question. If you were a city manager, you got to sort of think this through a little bit. If you were a city manager and you were in charge of keeping the streets free of ice, you have 3 options at your disposal. You have sand, SiO2, you have rock salt, NaCl, and you have ice melt, CaCl2. So from what you know, what's the most expensive out of all those? Ice melt. What's the cheapest? Sand. Okay, so I'm trying to keep the budget under control as a city manager. Would the temperature make any difference in what I use? Why would I use calcium chloride if it's so expensive as a city manager? I should always throw out sand, right? Adrian, you're shaking your head no. Why? It lowers the freezing point by 1 because SiO2, look at the periodic table. Where are Si and O2? Well, look at it. Where are Si and O2? Right next to each other. What type of bond is that? Right next to each other? Covalent. So it's not going to split. It's going to stay as one thing. Have you ever seen anybody ever thrown sand out and it melts and goes away? No, it just stays there, right? It doesn't separate. So it's going to lower by 1, by a factor of 1. What about salt? If I throw salt out, where's salt? NaCl. Where are they on the periodic table? Opposite sides. So what type was opposite sides? Ionic. So ionic is going to go into ions. What are the 2 ions it's going to go into? Na plus, Cl minus. So I have 2 things. It lowers the freezing point twice as much. Oh, what about CaCl2? What type of bond is it? Ionic again, far apart. You said it. There are 2 chlorines in this and 1 calcium. So how many total? 3. So it's going to lower the freezing point 3 times as much, right? Okay, so that's why. So if it's really cold outside, I'm going to use ice melt because nothing else is going to work. Okay? If it's sort of cold outside, I'm going to use salt. If it's not very cold, it's right around freezing, I'm probably going to use sand. Okay? So we're going to do some calculations to see how much each one lowers. Okay, what we just figured out, by the way, is I, which is the Van Hoff factor. This is the equation we're going to be using a lot, so you want to write it down. You want to put the information of what it is. We just figured out the Van Hoff factor. That's how many parts will it break into. Okay? K will be given to you. It's different for boiling and it's different for freezing. Okay? We're going to do some trials of what I would be. See if you remember. So glycol. Ooh, I don't know. What's the chemical formula? Doesn't really matter. It's a covalent bond. So it would be 1. So my I would be 1 for anything I don't know. Sugar, by the way, C6H12O6 is not got 24I. It's 1. I can't separate it into its ions. Okay? So it's got to be ions. NaCl. We did this. 2. It's ionic. Good. Okay, what about this one? I'm going to move this over so you can see this. We just did this one. 3. Okay, now I'm going to do a trick one. Hold up with your hands. How many you think this one's going to split into? Look at where it's at. I've got anywhere from 2 to 4 to 0. It's got to at least be 1. Right? I've got a 5, a 5, a 4, a 2. Okay, whenever I have a polyatomic, PO4, right, is a polyatomic. It's polar covalent. So I still can split it into its ions, right? But the PO4s stick together. How many PO4s do I have? 2. How many calciums do I have? 3. 2 plus 3 is 5. So the I factor here is 5. That's easy, right? Okay, so let's go on. Now, this is sort of saved from last time. So freezing point, depression, I'm going to be below the freezing point. So I'm going to end up being negative, and I've got the negative right here. I'm going to put the little highlights in. Water is the one that you're going to need to know a lot. Now I know on the paper that you've got, I think it says 0.51 for boiling point. That's okay. So there's a grid or a table that you want to highlight water. Remember that this is going to be a negative. Okay, this is going to be a negative on this side because it's below the freezing point. It's a freezing point depression. So I'm going to subtract it from the original freezing point. Boiling point is going to be above because it's boiling point elevation. So I'm going to add it to the boiling point to get the new boiling point. Okay, I'm still using this equation. Remember that M is molality. Molality is moles per kilogram. Okay, we're going to do some problems. You ready? KF is freezing. KB is boiling. We good? Okay, I've got all this on here. Okay, so as we're reading through here, they already told me it's 1 mole, so I can ignore that grams. 250 grams is what it's in, so I'm going to change that to kilograms. Okay, of water. What is the boiling point of the solution? So first thing I need to do is look up KB for water. Got it. Your table will be 0.51. It's okay. I'm going to use that equation. Delta T of boiling point is equal to KB times M times I. I've got to calculate the molality. How did I do that? I took 1 mole and divided it by 0.250 kilograms. Okay, everybody okay with that? So I got 4. Now I'm going to just plug into my solution and I get the change in boiling point. Done, right? No, what did I need to do? What did I say on the last page? I need to do what to it? Add it. It's going to be boiling point elevation, so I add it to the original boiling point of water, which is 100. Okay? So let's do another one real quick. And again, I'm going to put this up on the web, on the blog, so if you want to re-look at this, you can. So if I calculate the freezing point of a 0.29 molal sodium chloride water solution. So I've got my KF from the chart. I want to see how far I can depress this with 0.29. Plug in. Oh, wait a minute. How come ice 2? Sodium chloride. Sodium ion, chlorine ion. This is an ionic. Okay, so you got to remember the I. Okay, plugging in. I got 1.1. I'm done, right? Subtract it from 0, right? Because that's the original freezing point. So I'm going to end up with a negative. We're almost done. I know you guys are struggling here. Stay with me. Okay, so freezing point, we've got a concentrated thing. Now look, as I get more concentrated, the freezing point drops. So I could go out there as city manager and put tons and tons and tons of salt down if it's cheaper than doing the calcium chloride, right? But I got to weigh that option because the more concentrated, the lower freezing point I can get. Okay, so that's the end of this one. Let's look at your lab now. I want to look at your lab real quick. I think I've got one right here, except I need to. Okay. So here's the lab that we're going to do next time. Now, here's an incentive. Look at the back page of your lab. Application is what? Making ice cream. Oh my gosh, oh my gosh. If we get done with the lab quickly, we can do the application part. So we're not doing it today, we're doing it next time. So the incentive is to get everything done we possibly can today so that next time when you come, you can do the lab and then you can make your ice cream and then work on stuff. Sound good? Okay, so let's talk about what we need to do to get the lab done. Okay, so I am going to be passing out in just a minute a compound that your group is in charge of. Okay, and you're going to go through all of this. You're going to write the name of the compound. You're going to write the chemical formula. You're going to find out if it has an I and what the I is and how did you figure it out. You're going to research the cost. You can use your phones. You can use the computer if you need to, but you're going to research the cost. I don't care if you use it per pound, per gram, as long as you tell me the cost per something of mass. Okay? You need to calculate the molar mass of your compound. You need to calculate the number of moles. We'll be using 2 grams. So you need to figure out how many moles that 2 grams is. We're going to be using a total of 300 grams of water. Tell me how many kilograms that is. Then you're going to calculate the molarity. Now, or molality. Remember, that's going to just be number 6 divided by number 7. That'll give you number 8. That makes it easy. And then, why is it important to know the mass of the ice and the water? What are the 4 colligative properties, and what colligative property is being used in this lab? Now, when you go back to lab, this is all you're going to do. You're going to go back there. You're going to find your chemical, whatever it is, and it's not letting me draw. You're going to get a styrofoam cup. You're going to put it on a scale. You're going to weigh 200 grams of ice. You're going to weigh 100 milliliters of water into that, and each time you're going to stop and get that weight. Okay? Then, so this is a little messed up. Right on yours, it's a little messed up. I think it says water. It's supposed to say ice. So right here, change that to ice. And right here, this should be 200 grams of ice. That's still wrong. And this is 100 grams of water. So you're putting 200 grams of ice and 100 grams of water. So 200 grams of ice, both places here. Oh, sorry, I need to go back and fix that. So on number 2, it should say 200 grams of ice in your data table. And number 3, it should say 200 grams of ice and 100 grams of water. So each time you're just stopping a little bit and getting a mass, okay? You're going to weigh your solute, your salt sample. You're going to take your ice water and get the lowest temperature on the temperature probe you can get. Should be close to 0, hint, okay? Should be close to 0. So you're going to get that. Look at the page, the next page. You're going to put that freezing temperature right here, okay, right here at the bottom here. Then you're going to dump your mass, 2-gram mass of solute in there and stir, 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 stir. Get the lowest temperature it can go to, okay? If it starts going high again, you've gone down and now it's coming up, you're done. It shouldn't take more than 5-10 minutes, 5 minutes probably, to get that lowest temperature. When you're all done with that, you rinse everything off, you dry everything off, you get your stamp, you come in, you wash your hands, come in and make your ice cream. And then you come sit down. Now, once your ice cream's made, you are going to have to take the temperature of the ice water that made your ice cream and figure out what the molarity of the ice-salt water mix was that made your ice cream. If you make really good ice cream, you can get down to about -15, -17 degrees. So, pretty awesome. So what we're going to do today is fill in as much of this data table as possible. Okay, so as your team researches and finds all this stuff, you're going to tell me what chemical formula you used. What was your freezing point solution? Or you won't be able to do that. That's next time. Molality you should be able to figure out. That's number 8. You should be able to tell us the hazards, and you should be able to tell us the cost. So hazards, like anything that could be bad. I mean, I might get a really good freezing point depression with an I of 5, but it might be toxic to be around. Okay, so just do hazards and research it. Okay, yeah, you get cancer by this, or you can, don't worry, it kills pets and small children, but it really defrosts well. Okay, so we're going to get that up. I'm going to put this up on a different board on the, take a picture of it and put it up, and then I'll save it for you guys. But the more we can get done, the better today. Now, your team number for the first 2 rows is your yellow paper, your yellow person right here. For the last row, you are 6 and 7. 6 and 7. So I'm going to have you two go together and you two go together. Okay? Any questions? All right. I'm going to come around and give you your